Differentiable functions. So now that we have been able to find the derivative, we need to also set the conditions as to when a graph can be differentiated, as in, can we find a gradient? And this is very similar to finding out the limits of things and determining if things are also continuous. In other words, the summary of this entire video is that graphs have to be smooth and continuous at any point for it to be differentiable. So continuous means that there's no gaps. But what does smooth mean? Smooth means no sharp points, or as I like to say, pointy bits. And we'll see why in the example below. To determine mathematically if they are differentiable, we use limits, but instead of saying the limit as x approaches a value, we say the limit as the derivative approaches a particular value. So let's have a look at example 1. Consider the two functions below. Are they differentiable when x equals 1? In order for it to be differentiable at a particular point, the derivative as I approach from the left should be equal to the derivative as I approach from the right. So this section here for this graph, the limit as I approach 1, the derivative of this graph here, well, it looks like it's going to be, if we can look at that, the rise over run, 2 over, it's going down, so it's negative 2 over 1. But the limit as x approaches 1 from the positive side is a positive gradient. And by that same, it's a mirror, so it'll be 2. And because the derivatives are different, we can say it's not differentiable. It's not differentiable as the limit as x approaches 1 from the positive side does not equal the derivative as the limit approaches 1 from the negative side. In this other example, though, you can see here that you might be thinking, but hang on, that's the same thing. It's got a negative gradient on the left of 1 and a positive gradient on the other, with one small exception. The difference is, have a look here. There is a point and there is a smooth sort of curve here. This point, the derivative is equal to 0. This point, it's not flat. It's just a sharp point. If that had been flat, it would have a derivative. So at that point, the derivative, you could say, is undefined. So here, as I approach from the left, it's approaching a derivative of 0. If I'm coming in from the right, it is also a derivative of 0. These are differentiable because the derivative as I come from the left is equal to the derivative as I come from the right, as I approach 1. Example 2. For the function with the following rule, state the set of values for which the derivative is defined. Find the derivative for the set of values and sketch the graph of y equals the derivative of x. So I would dare say that this hybrid graph is probably going to have a discontinuity, as in a gap, but we shall see. So when x is less than 1, we have this negative graph here. So the end point for this one is negative 2, 1 plus 3. So negative 2 plus 3, which is equal to 1. And that's an open circle. It has a y-intercept of 3. So I can just draw a straight line. As for the other section, the quadratic, so when x is equal to 1, its endpoint starts at 4. We can see what the shape of the graph would be if we factorize it. And I think this will be the graph of x plus 1 squared. Yep. So that means its turning point would have been somewhere over in the negative side here. So it's just going to look something like that. So in this discontinuity, that section, the graph is not differentiable. So So I can say that the derivative of the graph is differentiable for all x as an element of R with the exception of the number 1. And then it says we need to find f, the derivative for this set of values, and sketch the graph of y equals the derivative. So we'll need to write a little hybrid function here. So the derivative of the first part will be 2x plus 2. I'm just doing the derivative of that equation. And the second one will simply just be negative 2. And this is x would be greater than 1 and x is less than 1. Please note here that, of course, there's no equal than or less than equal to signs because the derivative is not defined at either of these points. It does say we need to draw this. So from x is less than 1, we need probably some straight lines. It's just got a derivative of 2. Does it say that we need to do this on the same axis? I think it does. And sketch the graph. Well, we don't have to do it on the same axis, so may as well make a new set of axes so we don't get confused. So there is our derivative graph. And if we can compare, that negative linear graph just becomes flat, and there's the negative linear graph, which is going negative gradient negative 2, and then we've got this quadratic. When a quadratic we do a derivative, it becomes a linear graph, and that was the positive section, so we've got a positive graph, and all I've done there is I've substituted when x equals 1 for each of these derivative points. I've made sure to show that both of those points are not included. And that is the entire process of sketching a derivative graph for a hybrid function.